Now that we've simplified radicals, we will take and add and subtract them today. So general rule, you can only add or subtract like roots. And it's just like it says on the slide, just like adding like terms. So keep the root, add the coefficients out in front, and you're all good. Now in this case, there are no like roots. So we notice though that each of these has a perfect square in them and they can be simplified a little bit more. So let's go ahead and do this. We've got a 4 and a 2 here. We've got a 4 and a 3 here. And we've got a 9 and a 2 here. Cleaning it up, that's 2 root 2, 2 root 3, and 3 root 2. The like roots in this case are the root 2's. I add the coefficients out in front, which is 5 root 2 plus 2 root 3, and that one's done. So in this problem, we're asked to add if we can and then multiply. Notice in each parentheses, no like roots, so we can't add, so we're just going to take and FOIL these out. First, outer, inner, last, right? And we've got 6 root 12. We've got 3 root 20, 2 root 30, and root 50. Some of these can be reduced a little more, some of them can't. This one can. We've got a 6. I'm going to say that's 4 times 3. We got a 3, 4 times 5. This has no perfect squares in it, so I'll just leave it 2 root 30. And then this is 25 and 2. So clean all this up, bring the 2 out, that's 12 root 3. Bring the 2 out again, so that's 6 root 5. This is 2 root 30 again. And I bring a 5 out and 5 root 2. Look for any like roots, which we have none. So this is our simplified form. In this case, we have a radical in our denominator, but this time, if we were to take and multiply by root 7 over root 7, notice what would happen. This root 7 goes away, but I'd have to distribute that, and I'd have a 2 root 7 on the bottom, so that's not going to help. In a case where you have a binomial or two terms down in the denominator, we're still going to want to rationalize, but if we take and rationalize by something we call the conjugate, which is the same first term, 2 and 2, opposite of the second. We had a positive root 7, now we have a negative root 7. And then I'll take and multiply this all out. So I have a 10 minus 5 root 7. FOIL the bottom out, that's a 4. Minus 2 root 7 plus 2 root 7 minus root 49. And you'll notice the 2 root 7's reduce out, and the root 49 is just a 7. So this is 10 minus 5 root 7 over 4 minus 7, or 10 minus 5 root 7 over negative 3. Typically we don't like having a negative down in the denominator, so we'll take and bring that negative to the numerator. Still the same value, but we have 5 root 7, which is positive now because we're multiplying by a negative 1, minus 10, all over positive 3. So this is the same situation with the exception that we've got two terms on top, but we still have that binomial down on the bottom. We're going to rationalize by the conjugate of the denominator, which just so happens in this case to be the numerator. Won't always be. FOIL the top and bottom, so this is 25 plus 5 root 2 and another 5 root 2. And I'm just going to make this a 2 over 25 minus 5 root 2 plus 5 root 2, and that's a minus 2 in this case. Cleaning it up, I have a 27 plus, add the coefficients out in front, we've got a 10 root 2. Notice the 5 root 2, negative 5 root 2 go. This is 23. There is nothing that can be reduced, so that one's done. We move on now to rational exponents, or exponents that are fractions. So in this case, we have a base term a raised to the m over n power. That can be written in radical form as the denominator goes to the index, and the numerator is still the power of the base. So we've got the nth root of a to the m, which can also be written, as we know, of the nth root of a, all raised to the m power. And we're asked to simplify 16 to the 3/2. Now you can do that on your calculator, but I won't give you a calculator to do it on any kind of assessment. So we need to know how to do this without a calculator. So I'm going to take and convert this to from a rational exponent to a indexed root, because I know a little bit more about indexed roots at this point. So in this case, I'll put an index of 2, and I usually don't put that there because it's implied, of 16, and I'm going to raise that all to the third power. The reason why I don't go 16 cubed here is because the number is just too big for me to work out in my head. So I've got square root of 16 is 4, cube that, ends up being 64, and we're done. Likewise, now we're going to have a base raised to a negative exponent, so immediately I would change that to 1/27. I'm going to cube root that and take that to the 5th power. Cube root of 1 is 1, cube root of 27 is 3, and that's all going to be to the 5th power. 1 to the 5th is 1. 3 to the 5th is 243, I believe. Now we've got a fraction raised to a negative exponent, and again, I would do the same thing of take the reciprocal of the base, which is 8 in this case. Now I cube root it and square it. This one I could have taken and squared the 8 in the under the radical, but I typically like doing this better. So cube root of 8, 2, squared, 4, and we're out. This one's going to be a little bit different, and you'll see in a second. I've got 9 to the 2/3 power. If I cube root 9 and square it, it really doesn't do a whole lot for me. I mean, I can multiply this by itself, which is fine. I could have also written it like the cube root of 9 squared. However you want to do it, it's up to you. So this is a cube root of 81. Now, if I'm going to simplify that, I may not be able to do it as a singular integer or number, but I may be able to do it in terms of radicals. So in this, I know I have a perfect cube, 27 and 3. And from the 27, I get to pull out a 3. So 3 cube roots of 3 is the simplified form of this base raised to the 2/3 power. This one's difficult, and you may not see it that way right off, but you'll notice that I'm asked to multiply 2 roots. The only problem is my roots don't have the same index, so I can't just take and multiply 3 to the 9 and then make something up with the indexes. So the only thing I know how to do at this point is to change each into a rational exponent. So I have 3 to the 1/2 power, and then I have 9 to the 1/3 power. But again, we have the same problem. If I want to multiply these together, they have to have the same base, and they don't have the same base. However, 9 kind of relates to 3 in a way. In fact, I can rewrite 9 as 3 squared. It's an equivalent. And that's still raised to the 1/3. Now you'll notice here I have a base raised to a power, raised to another power, which means I can multiply powers. And lo and behold, I now have the same base, which means I can multiply these two terms together and add the exponents. So this is 3 to the half plus 2/3. Obviously, in order to add those, you're going to have like denominators. So this is 3/6 and added to 4/6, which makes 3 to the 7/6. I was asked to write this in simplest radical form. Putting this in radical form, I have the 6th root of 3 to the 7th. Now I can multiply that out, but I'm not going to, because if I'm going to simplify this, I'm going to need to break down that number. And since I have 3 to the 7th here, there's a perfect 6th in that. So this can be rewritten as 3 to the 6th and 3. Here's my perfect 6th, if you will. So I get to pull a 3 out, and I have a 6th root of 3 left. And that's going to be my answer. That's all we've got for today. Talk to you tomorrow.